So welcome everybody to Sierra Mountain Center Avalanche One online classroom. This is sort of the precursor to getting out in the field. There is an awful lot of stuff here for us to cover. In the past, we've talked about how a level 1 course could be a week long, and we still wouldn't cover everything we want to cover. So look at this as a starting point, a stepping stone to future learning, future discovery out in the mountains here. Thank you all for signing up with Sierra Mountain Center here. We are based in Bishop, and this is Emma. Some of you might well have spoken with Emma on the phone. She runs the office and manages programs and does a good job on that. No, we do have snow. This December, we've gotten good snow, and this is Rock Creek Canyon. We've got the first of our field sessions out at the moment, and that's just up in Rock Creek at the moment, doing avalanche work, beacon work, and looking at the snowpack and looking at terrain. We ran a program a week ago, and that's when all this snow fell. It was a fairly tough course, given the conditions were bad, but it's what we get. Generally we're hoping for snow. So this is my house a couple of days ago. By way of introduction of myself, I'm SP Parker. I'm originally from the South, the very deep South, New Zealand. Been living in this area since about 1980. Been running Sierra Mountain Center since mid-90s, and one of my full-time jobs is running the business. The other is guiding and instruction. Spent a lot of time out in the Sierra Nevada, doing a lot of ski tours, backcountry, climbing, and all over. So we've gotten snow, and there are avalanches happening at the moment. This is Wilson Butte area, just north of Mammoth, where we have quite a lot of things actually going on in this photo. And we're going to talk about a lot of that as we move through the next few hours online. So looking at this photo here, you'll see that we have a fracture line up the top here. We're going to talk about these later. This is what we call a slab avalanche. You'll also see down here, there's a couple of other layers. And this effect here is what's referred to as stepping down, where we have a small avalanche, it impacts a layer below, which in this case impacted yet another layer below. It's just putting more load as we get more disturbance in the upper layers, the avalanche moves. And you can see this here went all the way down to the rocks in the ground at the bottom. We do have a weak layer of snow at the bottom. And this is a cross section of a couple of days ago when we were up looking at things in Mammoth. You'll see we have a fairly distinct layer across the bottom there. And as we go through the next while, online and out in the field, you'll get to understand what this weak layer here is. And this weak layer is what has caused everything to fail next to the ground. There's also layers within the upper part of the snowpack, and that's what's given rise to these failures there. So there is lots going on in the snowpack. We often think that we need a deep snowpack to look at things. We actually don't. This here is probably about 40 centimeters or so of snow, 15 inches. But there's already, as you can see, 1, 2, 3, 4 different layers in it. So we're going to talk about things as we go through today. Once we get out into the field, and looks like some people have already signed up for the field sessions, then we'll decide where the best snow is and where we want to go. So when you come up for the field, Emma will send out an email saying where to meet, but we will be looking for the best snow, so be flexible in where we go. It's probably going to be the Mammoth area, but we might also go to the Bishop area, particularly if we get more snow, where we find the best, most teachable conditions. Went out with a couple of our guides last week, instructors here, Tyler and Alan. doing some tests in the snowpack. And as I said, there are things going on. In our tests, we found a failure layer, not in that layer of granular snow that I pointed out in a previous photo, but higher above it. And that's reflected in that other image I had of multiple layers failing on an avalanche near Wilson Butte, north of Mammoth. So there is plenty going on in the snowpack at the moment, and lots to look at, which is great. And the flip side of that is, from a practical point of view, it means that it is avalanche danger, and we need to be aware of it, assess it, and make good choices when we're out there in the backcountry. So as I said, we've started off great for this year. This is what we've got as of December, or the 5th of December. So according to this date, or that date, we're well above normal, which is good. On the other hand, last year in 2021, we got a lot of snow in December, about 9 feet, and then it just shut down for most of the winter until March and April. So it's anybody's guess. But of course, we all like guesses. So this is what National Weather Service is saying for the rest of December for us. So cold temperatures, but potentially above average snow. Whereas look at Alaska, above normal temperatures. And here we have January's outlook, where middle of California here, they're not quite sure. It's probably about normal, above normal, northern part of the country, below normal if you're down there in Southern California, and looks like Carmen Maria from San Diego. So that's the big picture. So let's get into our Avalanche 1 discussion here. As we go along, if anybody's got any questions, if there's something I can clarify, go ahead and mute yourself and just ask the question. You can wave a hand at me. Those of you who are on video, you can put a question in the chat box as well, and I'll try and get to those. But we've all been doing the Zoom stuff for a while. The more interactive we make it, the easier it is at my end. Probably the better it is at your end too. So our Avalanche 1 here is an introduction to risk management. Looks like some people want to go out and ski in the backcountry, mountaineer, board, whatever there. We want to have a framework in which we can make good, solid decisions when we're out there. As I pointed out, we already have an avalanche danger. So we want a system that we can work through rather than just a haphazard, well, I don't know, what do you think? So that's the goal here for us. We do have the AIRI online session here, and also the AIRI booklet is available here as well. AIRI is American Institute for Avalanche Research and Education. It's a nonprofit. It was founded back in the early 2000s. Prior to that, there's a lot of different avalanche courses around. They could range anything from an evening session up to 5 days or so for level 1. There's also the American Avalanche Association, and in the early 2000s, the Avalanche Association went ahead and tried to standardize the outcomes from a level 1 course. There's various providers, and AIRI is one of those, and we've adopted the AIRI curriculum. I've also adapted it and taken information from other programs, be it in Canada and other places such as Silverton Avalanche School, which I also do programs for. So I'm trying to combine things and get the best out of a number of different providers in order to give you the best program that we can. So I hope folks have gone ahead, found the booklet, and also the AIRI online session there. So I'll just put up this little poll here. since there's not many folks, no, just go ahead, tell me if you did the online session or whether you haven't gotten to it yet, just so we have an idea. Won't judge anybody. Who else? Okay. All right, looks like somebody had the dog eat it. Now try and do the online session, because everybody learns in different ways. And here we're doing the online. You've got the AIRI session online as well. You've got the handbook there, the booklet available, and then we'll get into the field and be able to do things there. A number of different ways. I'll also, at the end of the program here, give you some references for different books that you might like to look at and follow up with, again, and expand your learning and knowledge. So, as I said, the AIRI 1 is developing a framework and learning a process. There's other levels of your avalanche education. We will run over the avalanche rescue when you're up here. We need to do that before we head out into the field. However, there's also a full one-day avalanche rescue course that refreshes things, gives you more knowledge. We hope never to use the avalanche rescue skills, but like a lot of stuff, first aid, that type of thing, medical training, we want to be practiced with it so that if we have to use it, we're able to go ahead and do so. So that's a standalone program. Here we're talking about the recreational side of things, and beyond the level 1, there's a level 2, where you apply what you learned in the 1 in new situations. Another way of looking at this is at the AIRI 1 level, you're generally contributing to a group, and this is a discussion when you're identifying and recognizing things. At the level 2, we'd like to step it up a little bit and have people be a facilitator of a group, where we coach your application and you're doing more assessment and evaluation and attempting to manage the risk within your group. So a number of different steps that you can go through to start with, and we'll talk about that as we go along as well. In terms of today, we're going to divide up into a morning session and an afternoon session. In the morning, we're going to look at what we'll call the problems. And then in the afternoon, we'll go ahead and we'll talk about how we'll deal with those problems and our planning, preparation, teamwork, how we ride, and how we wrap up the end of the day. We'll take about an hour break at lunchtime, I hope, and then we should be wrapping up around about 3 to 4 o'clock, depending upon how verbose I am here. And we'll take regular breaks just to get up, stretch, and get something more to drink as we go through. Then when you come up here, we'll go out for day 1 in the field. We'll do, as I said, some rescue. We'll look at terrain, snowpack, route, and then we'll try and get out on a longer trip on day 2 and put it all together. We don't tend to go really deep into the backcountry on the field sessions because we don't want to spend a lot of time traveling. We want to spend more time looking at stuff and learning. So, it doesn't matter whether you're on a board, split board, snowshoe, skis, whatever. Distances won't be far, but we will be climbing, we will be getting around. The field days are not a ski, teaching day, so hopefully folks know their gear and equipment before they come up. So let's look at a few statistics here and know why are we doing all of this. This is some 70 years of data collated here. Overall, we can see that avalanche fatalities are going up. On the other hand, there's more people in the world, and there's more people in the backcountry. So yes, we would expect to see avalanche fatalities going up. We'd expect to see dips and rises, particularly with weather conditions. If there's not snow, well, there's no avalanches. 1920, avalanche fatalities went down because, as we all know, there was the whole COVID thing peaking then, and people weren't getting out in the backcountry as much as previously. So overall, fatalities are increasing. They're also happening to a lot of backcountry skiers. This again is our 70 years worth of data. When we look at things now, snowmobilers have very much come up in the rankings. Part of that is simply the ready availability of powerful snowmobiles that get you out deep into the backcountry fairly easily. In 1950, they weren't around. In 1970 or even 80, you might have a snowmobile, but you probably couldn't get the thing started. And no, they were just hellacious to deal with. Those have changed. And people are buying secondhand machines fairly cheaply. Climbers. Climbers often tend to be fairly oblivious about avalanche danger. They tend to think in the summer it's not a problem. It is, and we'll look at that statistic in a little bit later. There's also categories there for side country rider. Side country is a term that we're trying to get away from. It generally applies to where you, say, ride a lift at a ski area, then go outside the ski area boundaries into non-patrolled. The feeling now is that calling something side country gives people a false sense of security. Once you step outside that ski area boundary, really you're in the backcountry. Having ski patrol nearby gives people a false sense of security. And as we'll look when we talk about avalanche rescue, you've got maybe 30 minutes to try and get somebody out if they're buried. And by and large, you're probably not going to be able to get ski patrol on the scene within 30 minutes. It just takes them longer. So once you step outside that ski area boundary, you are in the backcountry. Now, hikers. Certainly in the Sierra, hikers here do die in avalanches in the summer and spring, but they're not aware of them. Ski patrollers. Ski patrol does the best job they can to reduce the risk within the ski area. However, we've also got a line there for inbounds rider. Ski patrol does a good job, but they're not infallible. And avalanches happen within ski area boundaries. So there are days, if I'm, say, skiing Mammoth Mountain, where I will wear an avalanche beacon. One of the first things ski patrol will do if they get on scene is turn their beacons to receive in the off chance that somebody might be wearing a beacon. So big powder days at Mammoth or any ski area, it's well worth wearing a beacon. So a lot of other fatalities there, but us as backcountry users in the winter are the primary group that suffers fatalities. Where do avalanches occur? As you'd expect, they don't really occur very much in those flat places in the middle of the country, where I'm told some people like to live, but I'm not quite sure why. They occur in the west, and they occur in the very far east. When we look here, Colorado has the majority of the fatalities. And other places such as Alaska, and then some of the states such as Montana, Wyoming, and Idaho also have a fair number of fatalities despite having relatively low populations. In California, we've got a big population, but our avalanche fatalities are relatively low compared to Colorado. There's reasons for that, and it's not just population-based. And we'll talk about that when we get into talking about weather. So hold that thought in your mind now about why Colorado has a lot of fatalities and why Idaho, Montana, and Wyoming also have quite a few. Time of the year, as you'd expect, January, February, March are the main months. However, we certainly get them during June, July, and August, during the summer months. And those people are probably going to be mountaineers and climbers who are exposing themselves to avalanches during those months. September and October, Fall, early winter also have avalanches then, even though a lot of the time there's not much snow on the ground and things tend to be fairly hard frozen. It just depends on the climate and the weather at the time. Age group, 20 to 30. 20 to 30. If you can get through a lot of different things during that time period, you've got a bigger chance of survival no matter what. As we all know, we take risks then, we're learning, we're still figuring out our place in the world. Again, these statistics can be a little misleading because there's not many people younger than 10 out in the backcountry. Overall, the fatalities are kind of creeping upwards as more people at an older age spend more time in the mountains, and it's more of a lifetime avocation for people rather than just a short burst. There's more people in the 20 to 30 age group out in the mountains. At that age group time, you've got no more disposable time, more disposable income potentially, and you don't have family, mortgage, kids, all the rest of the stuff. So, looking at it, looking at people online, if there's a few people who might fall into this demographic, right? So, just be aware that in a lot of ways you are at maximum risk in that demographic there. Looking at fatalities from last year, 17 total. As far as I'm aware, there have not been any this year, but I haven't checked the data recently. As we see, no skiers and no snowmobilers last year were more than skiers. Now, if we add snowboarder in there, which we probably should, they're equal. It's often said that there's 5 levels of learning. Obviously, all of you are here now, so you're outside of the bliss phase. Maybe you're in the terror phase where you don't know, and that's why you're here, and that's fine. I'm glad that you're here trying to get more education, more knowledge, more skill. What we've all got to avoid is the overconfidence phase, where we think we've got it all figured out, and we don't. Overconfidence happens in everything, not just avalanche education. I used to fly paragliders, and there it was referred to as the intermediate syndrome, where you got about 7 years of experience and thought you'd seen it all. That's when things go wrong. It doesn't matter what you're doing, whether you're using heavy equipment, running a chainsaw, anything that has potential to hurt you, we've got to avoid overconfidence. And we all aspire to become experts. Takes a lot of time, and we'll talk about that later as to what some of the standards for actual expertise are. And we all want to be Yoda. We all want the wisdom phase, but it's pretty hard to get to it. We've all gone through COVID and had to deal with that. And what I found is that there are a lot of similarities between what we do managing our avalanche risk and what we've done or what we still do managing our COVID risk. There's stay-at-home orders, and those apply to the backcountry as well, where the best thing to do is not go out or to choose the terrain you go out in. Same as you might choose the people that you go out with and create your own bubble. Choose partners with a similar risk acceptance, making your own bubble. We have something that's unseen that persists, and we can reduce the potential by wearing a beacon and wearing a mask. We can become educated. In both cases, we're assessing the risk, we're evaluating it, and we're mitigating it. As we know, everybody has different risk acceptance and different ways of mitigating it. It's up to you to decide how much risk you want to take and how far your risk mitigation measures want to go. And that applies to COVID, and it applies to avalanche risk. If you want to go out and party at bars and not wear a mask, that's fine. If you want to go out and ski steep in dangerous avalanche conditions right after new snowfall and a lot of it, that's fine too, but you have to accept that there is the possibility of either catching COVID or being caught in an avalanche. If you want to, hole up in the house or stay on the flats and just ski there, that's fine too. They're all ways of mitigating the risk and defining your own risk acceptance. For me, one thing, I don't want to get sick and I don't want to get caught in an avalanche. So particularly these days, I tend to be pretty conservative in both of those fields. We've all probably seen the bumper sticker that says no fear. Fear keeps us alive. We don't want fear to go ahead and paralyze us. What I would rather think about is respect and giving particular attention and consideration. We want to respect the environment that we operate in. And of course, everybody knows who this is, right? Even those of you in that 20 to 30 demographic, right? You all know who Aretha is. Some of this stuff is not actually that hard. Our avalanche danger, as we'll talk about, is rated between low and extreme. And what we need to overlay that with is the terrain that we go ahead and choose. Even when the danger might be rated extreme, and we'll talk about what that means as we go along, we can still go out. We just choose very simple low angle terrain. As the danger goes back towards low and is reduced, that opens up the possibility of getting into complex, steeper terrain. What we've got to do is be able to assess when it's good to go into that complex, steeper terrain. Then we want to also apply techniques that reduce our risk should there be something that we haven't seen. And we never have 100% knowledge. There's always gaps. That's why we apply good travel techniques as we get out there. We're going to use this graphic or something similar through quite a few different, at different times during the program here. Basically, again, when the avalanche danger is low, there's a lot of terrain open to us. As the avalanche danger increases, the amount of terrain open to us becomes more reduced. We'll apply what we'll call risk reduction measures. And we'll talk about that as we go along here. Then there's just going to be times going into terrain of high consequence where travel is just not recommended. Okay, you can do that, but you also have to accept the fact that the chance of triggering an avalanche and having a problem are significantly increased. For me, the bottom line is I want to go out into the backcountry and have a good backcountry experience, enjoy the mountains, and enjoy the environment. I want to keep doing this for as long as I possibly can. I want to keep doing this at least until I'm into my 40s, right? So are you laughing at me there, David? So, okay. I've been doing this for 40 plus years, 50 years now. I just want to keep on doing it. I want you folks who are younger to also have the opportunity to keep doing this as a lifetime, not just a one-off experience. If we're going to do that, the more we go out over here in this corner and roll the dice, the less our chances of having a long-term lifetime of doing it are. The more we push our risk management into the lower half of this, or that we're being divided across there, the more our chances of having a long mountain career are. As far as I'm concerned, any day in the backcountry is a good day. You're out, you're not in the city, and you're away from people, you're in a different world and different to what you might normally be in. I'm lucky where I live here. I've got snow, right out the window, mountains right out the window. I can be skiing within minutes if I want to. Not everybody has that opportunity. What we want to do now is get into what we'll call the problems. And we're going to start here with the avalanche danger triangle. Standard triangle here. On one side, we've got weather. On another, snowpack. On another side, terrain. Initially, we're going to start out talking here about the snowpack. So there's lots of different words for snow. How about in the chat box? Let's get people participating some here. Go ahead and write down as many words for snow as you can think of. No scientific terms, just give me a few snow words here. Type it on in. You can do it. Wow, yes, everybody wants powder, don't they? What else? Corn, sugar, slush, crust. Yep, indeed. All of those. So let's now go ahead and let's relate the snow that people just put in there. How about the weather that led to it? We're talking here about the best snow you've ever had. What was it? What was the best snow and what were the conditions that led to it? No, the powder, the corn, powder, high snowfall, okay. And okay, David's got no light, fluffy, cold, windblown, okay. Yep. So no, what we're trying to do is relate the type of snow that we're getting, whether it's good or bad, to the weather that created it. Okay, and what about the worst snow you've been out in? What was the weather that led to that? No, so far everybody's focused on the good, maybe slush and crust that was put in there. No, that's not so good. What was the weather that gave that slush and gave that crust? Cold, very windy. Okay, then we've got heavy, wet, and warm. Okay, the wet and the warm is what's leading to the heavy. So those are all snow that we get that isn't necessarily the best we've ever had, but it's what we've got. So again, we've got that relationship between the weather and the snow. We've got blizzard, whiteout, icy. Okay, if people are coming from the East Coast, icy is definitely a type of snow that you're going to get out there. So we know that snow is falling at different times, different weather conditions. And it's those weather conditions that lead to layering within the snowpack. Sometimes we think about the snow just being white on the ground. It's not. It's layered. And we have layers that reflect those different storms. In between the layers, we have interfaces, and those often represent the weather that happened between the storm cycles. So when we get out there, we'll be digging in the snowpack and we'll be looking for these layers because it's the ones with different characteristics that give us different layers of weakness or areas of weakness that can then lead to avalanches. So it's those layers with different characteristics of the source of avalanches. Give me a second here. I forgot some of my props. So our first distinction we're going to make here is when we have a weak layer on top of a strong layer. And that gives us what we'll call loose snow avalanches. I have here an Oreo cookie. I'm not just hungry, but often we want to think of the snowpack as being a series of Oreo cookies layered up on top of each other. With our weak layer on top of a strong one, we've got our cookie, and we've got this white indeterminate stuff on the top that we can probably push off fairly easily. There, that's what a loose snow avalanche is going to be. On the other hand, we also have slab avalanches, where we have a strong layer over a weak layer that is often sitting on another strong layer. And that's where we have our full Oreo cookie. And with a slab avalanche, we can push one hard layer off on top of a weak layer. And that's what gives us a slab. And we're going to spend a fair amount of time talking about slabs because 80% or more of recreational related accidents in the backcountry are caused by slab avalanches. So that's our first distinction: loose snow, slabs. We know that our layers are constantly changing. Here we have some nice bear tracks out of Taboose Pass, and we have changes at the surface where the bear walked and below the surface. And we'll go ahead and we'll define two different types of change. We'll call them direct weather effects, indirect weather effects. Direct ones are what happen at the surface. So in the chat box, type in some weather that you think is going to affect the snow at the surface. And while you're doing that, I'll take care of the Oreos. Wind, temperature, sun, yes, okay. We've got all those. There's one more. There's one more that we're missing. What do you think that might be? Weather at the surface. Okay. Precipitation. Yep, you got it there. Perfect. No, somebody put in, David put in rain. Rain's a subset of precipitation. We could have snow, we could have hail, we could have a lot of other things at the surface. So yes, we have wind. Temperature. So temperature and solar radiation are related, but they're not the same thing. Think of when we have warm nights, but the sun isn't out. And precipitation. So all those affect the upper layer of the snowpack at effectively our atmosphere snow interface. And one thing to consider is everything we see at the surface is one day going to be buried. So that's why we often spend time looking at the surface when we're out there, projecting ahead and thinking, how's it going to change? How things are going to be different in the future, maybe next week when we go out. And we'll talk about these as we go along here. Then we have indirect weather effects. And these drive change within the snowpack, below the surface. This is where we're going to just touch a little bit on some snow science, but we're not going to get really deep into it. So a couple of concepts here that we'll start with. Actually, before that, the things that drive that are air temperature and the height of snow that we have on the ground. Those are the two main drivers of change within the snowpack. So let's look a little more closely here. I've got a diagram that's got height of snow on one side of the graph and temperature on the other. Our first concept here is that our ground is always at 0 degrees centigrade. We're going to try and use centigrade since we're looking at things scientifically here. If you want, you can look at it in American and call it 32 degrees. So the ground is always at about that temperature. That is once we get snow on top of it. Snow is a very good insulator. The ground is always absorbing heat during the summer. We've got a certain amount of heat produced by radioactive decay under the surface. Once we get a layer of snow on top, that stops that radiation escaping into the sky, it insulates it, and it allows the ground to be at about 0 or 32. That's in our environment here, where we have what we call seasonal snow. This might change in Arctic, Antarctic regions there, but for us, that's what our ground is going to be. And that's crucial to the survival of plants and animals there. If it froze, then it'd be different. You might say, but I've been outside and have seen the ground frozen hard in November. That might be true, but that's before we get that insulating blanket of snow on top. And snow is a great insulator. That's why if you're stuck in the backcountry, digging a snow cave is a good idea. Snow cave will stay at about 32 degrees. No, it can't go much higher than that, otherwise it melts. So our ground is at 32. Let's just put a marker on our temperature side. Now let's add 50 centimeters of snow. Going to add 15 inches or so of snow there. Air temperature is our next factor that we'll consider. And we're going to call it minus 10 degrees in centigrade, or about 14 Fahrenheit there. That's what the air is, and that's what we've been getting at the moment. Temperature's probably less than that. Now, we'll put that on our graph as well. Now let's just draw a line connecting those two temperatures over 50 centimeters of snow. And we end up with a slope like this, where we're getting a lot of change of temperature over not very much distance. So everybody clear on that as we go along? Everybody good? Okay, let's change one thing. Let's add more snow. Now we're going to add 4 times as much, 200. Our ground remains the same, our air temperature remains the same. But now when we graph change of temperature over distance, we end up with a different slope angle. We don't get as much change over distance. And it's change of temperature over distance that's going to lead to one type of formation in the snowpack or a second type. Now, this is a very simplified graph here. In reality, as I said, snow is a very good insulator. And as we talked about, we have weather, snow falls at different times, at different temperatures as well. Once that's on the ground, because snow is a good insulator, it's going to end up preserving those temperatures within the snow over no greater or lesser periods of time. So in reality, our line might not be a straight one from ground to air. It might be more of a zigzag, reflecting slight changes of temperature within the snowpack. But this is just a simple version. And when we get a lot of change of temperature over distance, we go to a process that we'll call faceting. When we don't get a lot of change of temperature over distance, we go to a process that we'll call rounding. When I'm out there studying snow and digging a snow pit, I might well record temperatures and look for those changes within the snowpack. I'm using that to project forward to what we might get in the future, whether it might be a faceted type of crystal or it might be a rounded one. As you're starting out, you don't need to at all. But remember, there are changes within the snowpack. But the bottom line is a lot of change, we get faceting, not a lot, we get rounding. So what are these terms that I'm using here? Let's look a little more closely. We're talking here about snow metamorphism. Metamorphism just means change. From the sky, we get a snowflake falling. That snowflake lands on the ground, it undergoes change, and it becomes what we'll call a grain. Grains are what we have on the ground. Those grains can go through different processes, and what process they'll go through will depend upon our temperature gradient. A lot of change or not much. Faceting here is promoted by cold air temperatures and a shallow snowpack. So therefore we get a lot of change of temperature over distance. That leads to vapor moving through the snowpack, and we end up forming little sharp pointed grains here. In its extreme form, we go to these types of crystals, which are called depth hoar. Depth hoar is the extreme end of faceting. It happens when we have cold air temperatures and a shallow snowpack for a prolonged period of time. We don't often see really good things that look like this. More often we see it looking like this one here. So this is the faceting process promoted by cold air, temps, shallow snowpack. Let's see if I can get this to work. So we get vapor moving, it grows onto that original snow grain, and over time it can end up forming this cup-shaped crystal or grain. The thing about these is that they bond poorly to each other. It's often referred to faceted snow as sugar snow. It looks like sugar, and you can end up pouring it from one hand to another. You can squeeze it, and that's often our big test. Take it, give a squeeze. If it forms a snowball, it's probably not faceted. It's the other type, rounded. When we look at things under a hand lens, we might see these little growth lines on it. And this is our extreme form of depth hoar there. So depth hoar forms at the bottom of the snowpack. And we can often go ahead and see it. As I said, we can try and make a snowball. We can squeeze. If it doesn't form a snowball, it might well be facets. Complicate things just a little bit. Depth hoar forms at the bottom of the snowpack, but it's not the only place where we can get faceting. We can get faceting near the surface, where near to the surface, for a number of different reasons, we might get a strong temperature gradient with a lot of change over distance. Then we end up with near surface facets. And that's what we're getting at the moment. The grains, again, are going to look sharp. We might squeeze them. We probably can't make a snowball with them, but they're not at the bottom, they're at the top. However, when we get more snow on top of this, then this layer gets buried more deeply. And as we talked about, it's like sugar, grains don't want to stick to each other, so this ends up creating a weak layer within the snowpack. And right now, we're getting facets occurring near the surface because we've got very cold nights that are promoting it. So there's a lot going on here. So we'll develop it as we go along, but let's go into our next type of process, which is rounding. Again, we've got our crystal falling from the sky. It loses arms, it becomes a grain, and those grains just continue to grow and become more rounded. And this is promoted by warm air temperatures and a deep snowpack. And these rounded grains might look more like this. They tend to stick to each other. They grow, such as here, what are called nets between the grains, and that bonds one grain to another, which tends to lead to a more stable snowpack. So in terms of for us as backcountry users, we'd like to see rounding within the snowpack. From us, again, for backcountry user looking for stability, we don't really want to see faceting, but the bottom line is we're going to get it, simply because we have cold periods with not much snow, particularly here early season in the Sierra Nevada. So faceting leads to what we call a persistent grain type. We'll talk in a little bit about our avalanche forecast. And the avalanche forecast often talks about persistent grains. So facets are persistent grain. Depth hoar is our extreme end of faceting. There's another type that we'll talk about right now that's persistent, which is surface hoar. Surface hoar is kind of the frozen equivalent of dew. I saw some day before yesterday when I went out scouting conditions up around Tom's place. It's little feathery crystals that grow up from the surface of the snow. When we look closely, we can often see a lot of little Christmas trees. They're pretty cool. Sometimes they can get to extreme size like this. It's about 5 centimeters. It's happened over several days. You can see different growth lines, 1, 2, 3, 4 of those there. Surface hoar, when it's at the surface, is not a big deal at all. It's generally when we get surface hoar buried, such as in this photo here. There's a buried layer of surface hoar. Imagine it's little things that stick up from the surface. Now we get more snow on top of them. They're still sticking up. Something can disturb them. They can all fall over, create a weak sliding layer. With any of our persistent grain types here, they can form fairly quickly. Depth hoar takes longer. Facets can form fairly quickly, especially at the surface. Surface hoar can form overnight. However, to get rid of them takes a lot longer time. That's why we call them a persistent grain type. And our problem becomes when the surface hoar, in this case, gets buried. Right here, we can see a layer of surface hoar there. As I said, that can go ahead. It forms a weak layer. All of our little Christmas trees that were standing up fall over, and then they're just a sliding layer where everything can move. So we're keeping track of when these sorts of things form because they're a weak layer within the snowpack. So we want to be careful and find out where they are. We can also get what we call grappel, particularly in the Sierra Nevada. This can persist for a period of time or can go away fairly quickly. They're little frozen balls of snow. They're kind of the snow equivalent of hail, but they're round balls that don't stick to each other. Don't confuse this with our rounded grains within the snowpack. Those do want to stick to each other. But the rounded grains within the snowpack are a secondary feature, not a primary one. And these here are a primary feature falling from the sky. Rounded grains within the snowpack are not a primary feature. They formed within the snowpack. So don't get too confused there. This is data from Canada and Switzerland, where they've looked at weak layers, and by far the majority there in both of those places were surface hoar. Facets, of which depth hoar is the extreme end, were further down the list. We don't have to deal generally with a lot of surface hoar in the Sierra Nevada. Other places do, particularly mountain states. And we'll talk about that as we go along into the next presentation. So facets and depth hoar are often the problem that we have to deal with in our snowpack, which is why we look for it, we identify it, we track where it is. So faceting and rounding are metamorphic processes. They happen. Nothing we can do about that. But they can create or reduce the avalanche hazard for us. The more faceting, the weaker the snowpack, the more rounding, the more stable, for lack of a better word, the snowpack. So is everybody good on that we've talked about so far? Any questions? There's a lot of stuff going on out there. So no, please ask away before we delve more deeply. We don't have to go more deeper than this into the science. We do on other things though. Okay, all good? Let's keep on going, talking about our snowpack. That's our background info on them. Now let's think about what we'll do when we're out in the field looking at the snowpack. We're going to make observations, we're going to gain information, and we're going to look at the snow cover, the layers within it, and how well those layers are bonded to each other. Sometimes we're going to do formal observations, but digging a big pit like this takes time. More commonly, we're going to go ahead and do informal ones and do quick assessment along our way. If we get something in our quick assessment, then that might trigger us to dig more deeply in the snowpack. A lot of people think that whenever we go out in the snowpack, we've got to dig a snow pit and look at the snow. We generally don't have to. I dig them when I need more information. We will, however, go ahead and dig them when we're out there, primarily to give everyone an idea of what's going on in the snowpack and what to look for and what the actual snowpack is. So the snow pits are useful. They can help our understanding, but there are issues that we need to remember when we're digging a snow pit. It's a very small snapshot of a big picture. They only give data as deep as we dig them. Variability of the snow cover is always an issue. So we dig in one place, we'll get one amount of data. We don't know what's happening in other places. And we can't transfer the information to different elevations, slope angles, aspect, and so on. So we don't want to put all our faith in one pit that we dig. Generally, when I'm out there, I go ahead and rely more upon my informal information gathering, because I can do more of that faster in more places than I can doing formal snow pits. But one of the things that we will look for when we're out there is a hard over soft layer. So like our Oreo cookie, we're looking to see if we can find a soft layer with hard over the top, which, as we just talked about, is a slab, which are related to 80% of recreational accidents. So that's one reason why we might go ahead and dig a pit and look. If we find something in our snow pit, that might be our trigger to go a little further and do a test to actually quantify how well things are sticking together. Let's say we get a result in our shovel compression test here, which is scored from 1 all the way up to 35. Then we decide maybe I'll do a bigger test and put an actual person on it. And this is what is called a Rooch block. And this is scored from 1 to 7. 1 being it fails when you dig it, 7, it doesn't fail after multiple jumps on it. So we're scaling up our investigation. And sometimes we might get a result like this. And right here, we have our Oreo cookie. We have a hard layer here, a soft layer in between the two, then the hard layer on top, which is our slab. So we're looking for these sorts of things when we're out there. As I mentioned, with a snow pit and doing our tests, they're not transferable and they're not giving us the big picture. We have to deal with what we call spatial variability, which is the change of snow over terrain. Now, this is a study done in Canada a number of years ago. And here they dug a large number of those big Rooch blocks. A Rooch block is 2 meters wide by 1.5 high. So an awful lot of digging. Probably on this study, they had a bunch of undergraduates to do it. So, as I said, it scored from 1 to 7. 1 means it fails as you dig it. 2 means it fails as somebody steps onto it. 6 means it fails only after repeated jumps and moving further and further down the block. So on this study here, they found everything ranged between 2 and 6. So let's say we went out and dug our snow pit here, got a result of 2, we'd probably go, oh my word, look at that. On the other hand, we dug it over here, a few hundred, 100 yards away or less, we got a result of 6. And we go, oh, it looks pretty good to me. Not seeing any instabilities in the snowpack. So where we dig our pit really, what the results we get might well depend upon where we dig the pit. So what we tend to do is we don't place our faith in the big numbers that we get. We place our faith when we get a small number over here, much more. It's kind of again like COVID. Just because we get a negative COVID test doesn't mean that we don't have COVID. We still might. We got a negative test. It's generally the positives that prove things, not the negatives, because we often get what we'll call false negatives in COVID and in SNOPE work, such as a 6 here, whereas a 2 might be more representative of the problem we're dealing with. And this is what we'll call uncertainty. And when we're out there, we have to recognize that we don't have 100% information. There are things we're uncertain about. So we want to stack the odds in our favor where we can. We'll get into this a lot more when we get out into the field. As I said, a lot of the time, I'm going to go ahead and use informal data gathering rather than formal. Now, what's the snow feeling like under my poles? Well, under my skis. I can take my pole and I can push it in there and see if I feel a hard layer on top of a soft one. It's hard to get in, then boom, it goes suddenly. I think, oh, that's a harder layer over soft. I wonder what's going on here. That could be my trigger to pull out my shovel and look deeper in the snowpack. Or I may go ahead and pull out my probe pole. The probe pole's just a finer, better tool than using your ski pole. I can take that and I can push it in and I can feel those hard layers. I can feel those soft layers. So that's a good, quick way to go ahead and find layers below the surface. Now I'm asking myself, is the snow compacting? Originally the level of the snow was up here and it's gone ahead, compacted down. Air has moved out of the snowpack, been squeezed out. The grains are starting to stick to each other. Cracking in the snowpack. That means there's a weak layer underneath that has gone ahead and failed. So right here, it started from the ski pole and cracked all the way down slope here. There's been a failure below the surface. This should be a red flag and a warning sign to you. It could be a trigger where I decide to go ahead and look and find out what that, or trigger for me to go ahead and investigate further. What is failing down there? We'll talk a little bit about avalanche report, but it's a good place to be able to relate back to the avalanche report and what was found in that. More cracks here. This is obviously something bad is just happened or going to happen. So I want to be very careful when I see cracks like this. I can go out and I can jump on little windrolls. See how easily those break. We'll talk about wind in a little bit as to why we're interested in these. Okay, it doesn't take anything for me here just to move out, jump on something, see if it breaks, and this is an indication that possibly a slab. When I'm touring around on my skis, often I'll make kick turns to bring me back the other way. At this point, right in my kick turn here, I can do a little mini roosh block. I can just get there, I can give a little push, jump a little bit and see if I get any fractures or failures there. I can go out on a small test slope and go ahead and just ski that and see what happens. A very good one to do is what we'll call a shear block, where I go ahead, make a little square, put my hands behind and pull and see what happens. I might do this when I feel a layer down there with my pole. Then I go ahead and I ask myself, I wonder how well that layer is bonding to what's underneath. That's when I can just pull off to the side, do my little shear block test. It's quick, it's fast. I can do it while I'm waiting for people to catch up, or more likely, they can do it while they're waiting for me to catch up to them. I'm asking myself, is it wet? Is the snow wet or dry? What are the temperatures like? If I'm warm and I'm taking off clothing, the snow is also getting warm. And snow does not like to be warm. It likes to be cold, as opposed to us. Anytime snow is around about its melting point, it's losing significant strength. It doesn't like to be close to 32. So there's a lot of different ways I can gather information about the snowpack when I'm out there. And all of this, I can make notes or I can store it in my head. But what I'm trying to do, identify what we'll call some red flags here. We think about a lot of snow as being a problem. Often a lot of snow is not the problem. It's a shallow snowpack that's the problem. Because a shallow snowpack tends to be more variable. As we talked about, when we have a shallow snowpack and cold temperatures, that's when we get faceting. Faceting is weak. So anything less than 1.5 meters we'll call a shallow snowpack. We're asking ourselves, is it weak? Are there those layers within it? Or are there faceted grains? How variable is it? Are there strong over weak layering? Strong over weak is our slab. Is it a near freezing? As I said, snow doesn't like to be warm. And do we have some of those persistent grain types? The 3 primary ones being facets, depth hoar, which is extreme faceting, and buried surface hoar. Remember, surface hoar is not a problem when we see it on the surface. It's a problem when it gets buried by the next snowfall. And then if we do some tests, is our compression test less than 20? It'll make more sense when we actually do this. Is our root block less than 4? Do we have smooth, clean surface failures there? We'll look at our plane where things break. If it's rough and irregular, that's not so much of a problem as a smooth and clean one. But if we don't want to dig into the snowpack, we still have information we can gather informally about snow cover and layering. If we want to go more formal, then we can incorporate our test results there. David, good question, and I should have clarified that. Is it possible for rounded grains to change to faceted grains? Yes. We're not looking at an end result here. It can go one way, it can go back the other way. It's always going to depend upon our depth of snow and our air temperature. As we go through the winter, we generally hope for more snow to build up on top, so we get more and more depth. So we're probably going to move more towards the rounding phase. Early season, that's when we get shallow snowpack, cold temperatures. However, say last year, we ended up with no more snow being added throughout the winter. So our snowpack continued to get weaker and weaker and weaker because it faceted and faceted more. So yes, it can go either way, back and forth, just depending on the prevailing conditions. So thank you for asking that, because no, I should have clarified it. We'll call weather a problem. It's one of the things we have to consider. We've already talked about how the weather at the surface gives us our direct weather effects, and then indirectly, the weather gives us our changes within the snowpack there. We talked about how we're dealing with weather, with precipitation, wind, temperature, and solar radiation. Of all of these, wind is our biggest concern in a lot of ways. Wind is one of the big architects of avalanches because it moves snow from one place to another. It scours it, it deposits it. Where it deposits it, it tends to mechanically bond one grain to another. The wind pushes them together, they're mechanically bonded, and that's what forms our wind slab. Again, wind slabs, 80% of accidents. So wind is the big architect of avalanches. We're always paying attention to wind. We're looking where the direction is coming from. We're looking where the snow is being scoured. We're looking where it's being deposited. And there's different clues we can use to give us that information. And wind is what forms our slabs. Precipitation. Are we getting snow or are we getting rain? And that's going to affect our layer interfaces. What we're getting now, a lot more are rain on snow events, and that's a function of climate change. And this is becoming more prevalent, especially in the Sierra Nevada. And that is changing the way we think about snowpack here. So this is a rain and snow event a couple of years ago. We won't get into all the reasons why, but no, basically rain is warm, snow is cold. And the rain tends to warm up the snowpack, it tends to saturate it, it adds more load to it. So this is something that's changed over the last decade or so, and something that we really want to pay attention to more and more. As well as precipitation, sun. Here we have what we'll call sun cups. This is an extreme form of them. This is going more towards what we call neve penitentes, which are pillars of snow sticking up, the result of the sun forming a little solar oven down in here where the sun ray or radiation is reflected back and forth. Dirt tends to absorb radiation too and exaggerate the effect. We didn't used to see these neve penitentes in the Sierra Nevada. We are now, especially after a long period of clear, warm weather. Temperature, as said, it can be warm at night. The snow doesn't freeze overnight. It just continues to warm and warm and warm to get softer and softer. The sun will give us this sheen on the surface, a sun crust. All things that we'll take a look at. All of these direct weather effects at the surface are going to form layers that will be buried. How well do you think the next snowfall is going to stick to this? Maybe not very well. What we'd like with our storms is for them to come in warm and then get colder. That way, this layer here might still be a little sticky. The warm snow adheres to it, and then it gets lighter as it goes up. Sometimes we'll have what we call an upside down snowpack or upside down storm, where it comes in cold and gets heavier as it warms. There we've got this layer might be frozen. The cold snow, light snow, won't stick to it, but we get more load as the storm warms. So that's something to watch out for as well. So we'll think about how future storms are going to adhere to these layers. Whether we can get information before we leave home. We can pull up National Weather Service or whichever your favorite weather source might be. But I'm always looking at the weather, probably too obsessively. For folks who ski around Mammoth Mountain, Mammoth Mountain Patrol has gone ahead and changed their site now. But if you put in Mammoth Ski Patrol, it'll take you to this site here. It'll give information for the bottom, all the different chairs on the mountain with current, wind speed, direction, wind chill, temperature, all that sort of thing there. And this is fairly useful, but only for Mammoth. There are other weather stations throughout the mountains. Some of those are a little harder to access, but those are good information. So we're asking ourselves what's happening now and what's happened in the past. I mean, has it snowed recently? How much have we gotten? Now, this is kind of what we'll call our out the window forecast. We're asking ourselves, has it been windy in the past and is it still windy? Where has the snow picked up or the wind picked up snow? If it's picked it up someplace, it's put it somewhere else. And we're always interested in where it's put it because that's our slab and we are paying special attention to slabs. In California here, most of our storms come from the west, southwest, somewhere in that area. The Sierra Nevada isn't a north-south range. We think about it being so, but it isn't. It's more of a northwest, southeast. So we're always interested in how Our storm is interacting with our mountain range. For us in the Sierra Nevada, we get maximum precipitation when the storm comes from more the southwest and hits the Sierra Nevada at right angles. How those storms hit the mountains will affect our wind directions. We'll have our prevailing wind, but then that's always going to be affected by the local terrain. And we have to assess that locally when we're out in the field. When we look at weather here, this is taken from Windy. This is at the surface. We have wind going in a lot of different directions, particularly close to the ground or at the ground level. As we go up in elevation here, now we are at 6,500 feet. The wind's becoming a little more consistent. Then when we get all the way up to 40,000 feet, the flow is no longer affected by the terrain. It's this upper level that really affects the big weather picture. It's the surface that affects our local picture. So we're always thinking for us as backcountry users, what's our effect of weather at the surface and what can I see in particular? When we're out there in the backcountry, as I said, we're always looking for signs of wind. What we have along a ridge crest here is what we'll call a cornice. A cornice is an overhanging lip of snow. This is formed by the wind blowing from the right. It picks up snow out here on the right. It goes across the ridge crest and then it deposits it over on this side. The cornices are formed by wind coming over the lip and vortexing, eroding, and depositing snow. They overhang out over there. Every cornice has its day. Every cornice falls off sometime. And we'll talk about that when we talk about our avalanche danger. We're using the cornice to indicate our wind direction. And we know that over here is going to be where the wind is picking up snow. We'll call that our windward slope out there. Over here, the wind speed drops. Snow falls out of suspension in the wind, is mechanically bonded one grain to another. And this area here is where we're going to get our wind slab formed. Unfortunately for us, as skiers or backcountry users, this is often where we might have the best skiing. There's the most snow, maybe it's the most powdery, but it's also potentially the most danger. So two things going on in this picture. We've got the cornice, which is a potential danger. We've also got the wind slab formed down here, which is also a potential danger. So those are our indicators of wind direction. Where we don't have a ridge crest that forms a cornice, we'll often get deposition of these little arrows of snow sitting behind obstructions like these. This is our indication the wind is blowing across slope here. It's blowing from right to left and depositing these. So these are all of our clues as to what we're getting for wind direction. Wind can move snow up to 10 times the rate it can fall from the sky. And that's kind of our problem. Okay, we've talked about wind direction. In this photo here, where do you think the wind is coming from? Type it in the chat box there for me. Where has it been blowing from? Other side of the ridge we can't see. Got it, yes. Blowing this way, the cornice is always formed downwind. So those are our clues that we're looking for. Again, like we did in the snowpack, we're gathering clues and information, and we're coming up with some things that should get our attention. In the precipitation, is it rain or dense snow? Again, things don't like to be close to zero. The quantity of snow, we're going to put a number of that on that of 2.5 centimeters, about an inch an hour. 1 hour of that doesn't matter. 12 hours, giving us 24 centimeters, going towards 12 inches of snow, then that should get our attention. With wind, we don't care about the direction so much, the cardinal direction. We're interested in, is it putting snow onto slopes where we're headed? How strong is simply, is it moving snow? If we can see snow being blown, then slabs are probably being formed somewhere. With temperature, again, back to our freezing. Snow doesn't like it, and rapid changes. Snow is a remarkable substance. It adapts well, but only to slow change. It doesn't adapt well to rapid changes. And with radiation, strong radiation for a long period of time. Again, no snowfall, a little bit of strong radiation for a short period of time, doesn't matter. Lots of steady snow for a long time, steady sun for a long time, also bad. So these should all get our attention there. And this doesn't take too much other than keeping our eyes open and our brain active. So any questions on weather from anyone as we move on here? Let's see. How did you know 2 slides ago the wind was right to left from David? Let's go back here. Which one are you talking? This one, David?
The next one.
Going that way? This one? Okay. We've got the bigger arrows on this side. There are some little ones on this side, but the biggest ones are over here. We're getting some deposition on this side, but primarily the biggest arrows are on over here. Say up here. There, we've got arrows going that direction. We've got that in behind that tree there. So this is fairly subtle, but it's something to develop your eye for when you're out in the backcountry. And we'll be working on that when we're in the field, asking you, where do you think the wind's been blowing from? Also, what you can't see in this photo is the big picture. We know in the Sierra Nevada, most of our storms come from the west, and the big picture here that we can't see is that west is actually to our right as well. So I'm not just looking at this, I'm adding up larger scale as well. Good question, thanks. All right, so those are our red flags here. We'll just store all of this in our brain or we'll write it down.
Sorry, I had one question.
Yeah.
The mechanical bonding from wind, that's different than what like an indirect bonding through the snow layer would be, right? It was just kind of forcing it together.
Correct. Yes, it's a mechanical bonding, not say a chemical bonding, such as we might have with our necking process with our rounded grains that grow towards each other. They're not getting squeezed, they're actually growing to join.
Okay, thank you.
Good. All right. So snowpack climates. This is a big, broad definition that we have maritime, continental, and between those two, we have intermountain as it stands in the US. Maritime climate tends to be typified by deep snowpack, warm temperatures. So overall, type it in the box there, what type of snow grains do you think are going to be created below the surface with our deep snowpack and our warm temperature? What do we got? Who's going to do it? Rounded grains, correct. Yes. So we have relatively uniform layers. We often have a quick danger rising, then a quick fall there. Continental, a shallow snowpack, cold temperatures. So what type of grains might we get here? Type that one in for me if you would. Faceted, yes, got it there, folks. So shallow snowpack, cold temperatures, often variable. Often in our continental environment, our danger is very slow to fall. Then we have our intermountain, which is often a deep snowpack later in the season, shallow early, cold temperatures, and we likely get variable layering here. Faceting early, rounding later. Often a quick to rise danger, slow to fall, depending on the season. Intermountains might be somewhere like the Wasatch Range. The Sierra Nevada is probably a typical maritime. Idaho, Wyoming, Montana, a typical continental. As we talked about with our initial data, those places tend to have a fair number of accidents, and that's because of a lot more faceting, a shallow snowpack, a variable snowpack, and a danger that might be slow to rise and very slow to fall. So that's why people often tend to get caught in avalanches more in the continental environment than we do, say, in our maritime environment here in the Sierra Nevada. So that's relating now our big scale weather patterns back to avalanche fatalities and deaths. When you get into deeper into snow science, there are specific parameters that will define what a continental snowpack is, such as number of days with specific temperatures, that type of thing. Here in the Sierra Nevada, we do get some canyons that have more, let's say, intermountain aspects than other ones do. The west side of the Sierra Nevada is typical maritime. The east side, some parts we can call maritime, some we might call more intermountain. So these are big, broad definitions here. So that's our presentation on weather. We're now on to the third side of our triangle here, the terrain side. We've done weather and we've done snowpack. Terrain. There's lots of things that we can't control. However, there are things that we can control, and that's where we go and how we do it. So we're going to talk about the where a little bit later. We'll talk about the how. One of the things that we do want to be able to do is to be able to recognize avalanche terrain. If we can recognize it, then we can go ahead and choose terrain there where we can reduce our hazard. This is the Sherwins here out of Mammoth. This is what we'll call fairly complex avalanche terrain. This is a popular ski area. Lots of runs here. It's very close to the town of Mammoth, so it is a popular area. There have been avalanche accidents in here. And if we go to this area during the field days, we'll be talking about those. But there are two primary things that we want to think about when we look at avalanche terrain. That will be slope angle and aspect. Slope angle plays a large role in whether an avalanche will release. What we're talking about here is what we'll call the start zone, where the avalanche will originate. If the slope angle is too shallow, it's not steep enough for the snow to slide on under the effect of gravity. And that's generally less than 25 degrees. If it's too steep, the snow continually slides off and it never builds up enough to accumulate a slab. And that's generally over 55 degrees. But in between 30 and 45 degrees is the prime range for slab avalanches to occur. And that's what we'll focus on as being effectively our prime range. The very sweet angle is probably 37 degrees. Our problem if we're skiers and snow and riders, boarders, is that 30 to 35 degrees is often where we want to go ahead and be. That's also in our prime range. So we're constantly going to evaluate slope angle. There's a lot of different ways we can do it. We can use online tools, and these are handy. For the field days, when you come up, we will be giving out maps and so on that will give us an overall view of the terrain. Remember that the accuracy of these online tools depends very much upon the data, where they're drawing it from, and the resolution. Most of the resolution that's used is around about 90 feet, which means you can still have a steeper section of about 80 feet hidden within that. Newer tools are starting to improve that resolution. I normally use CalTopo, but there are other ones around, and we'll talk about those later. So that's a starting point for slope angle. More critically, I think, is being able to evaluate it when we're in the field. Most people will go ahead and overestimate slope angle. A lot of people will say that they ski 45 degrees. 45 degrees is really steep when you're at the top of it. And you're probably thinking about how are you going to get down it. Looking at slopes on Mammoth Mountain for where people might be familiar. Most of them tend to be in the 30-degree, high 30s, which again is close to our sweet spot of 37 degrees. Cornice, the lower section of that is 28 degrees. And a lot of the run-out zones and the paths are going to be in the low to mid-20s. So for people who know Mammoth, that's handy. President's Weekend in 1986. Avalanches started up here in Cornice. They ran all the way down here, all the way down, and they were able to damage lift towers down here on Chair 11, Sesame Street, for people who know that area there. So Cornice, the fractures up here were probably about 20 feet thick, top of Cornice Bore. So that's our angle. Then in terms of aspect in relation to the wind, this is our primary one in terms of aspect. We've talked already about our windward slope and our lee. Snow is picked up on the windward, deposited on the lee. Down here is where we get our cornices formed above that lee slope as our indicator of direction. This here is what we're going to call top loading or lee loading, where the wind in this image is blowing from left to right. We can also have the wind blowing across a slope, and that's what we're going to refer to as cross loading. Here we have a series of mini windward lee, windward lee, windward lee. Over here we get snow deposited on that slope, and that's where we'll get a slab. With cross loading, we can get a series of slabs here as the wind blows across that slope. Here we have a series, or we have snow, no snow, no snow, more snow over there. This could be formed by either wind blowing across slope, or it could be formed by sun. When you look at this image here, you've got to look a little closely. What do you see that tells you that this might be the result of wind? Look carefully and think about what one of our wind indicators might be. Type it in the box there for me. What do you see? A mini cornice on the ridge. Yes, right along there. Yep. So that's what we've got blowing across. So it's windward lee as it blows across slope there. Let's go back. Now we've got it. So a whole series of windward lee slopes there. Okay, when you look at this one, where do you think the wind's been blowing from here? Look for those indicators that we talked about. What do you think? Type it on in. Left to right. Okay, yes. We've got these little pillows of snow, these little arrows behind objects. So we've been moving left to right. It's also deposited what we'll call a pillow of snow in here, there. This is just outside a ski area. A charge has been put in there, and you can see it's fractured all the way around there. So this is about to start sliding down. It's a result of cross-loading moving over this way. Again, this emphasizes here the problem we have as skiers and riders. We don't want to ride and ski out over here. It looks terrible. So we automatically think this is where we want to go. And yes, it's also where the snow has gone, and it created a slab, which is a potential hazard to us. So we want to just look at the ski run. We also want to assess the avalanche path here. When we look at this one here, where do you think the wind had been blowing from in this photo? We've got actually two answers here. Look carefully and type it on in for me. What do you think? This is Red Mountain, just north of Tom's Place, south of Mammoth. So what do you think for here? Behind the ridge? Yep, okay. That's one of the answers there from Carlos. What's another answer? Yep, we've got a cornice up top. Left to right, yes, correct. Because we've got little cornice along here. So it's been blowing over the top, but it's also been blowing across there. We can see snow has been removed here, deposited there, removed there, deposited there. So the wind is not always blowing from one direction all the time. It can change. So that's something we want to be aware of in our evaluation. So our two primary things that we look at are slope angle, relation, and aspect to the wind. Those are the two primary. We have secondary ones as well. An aspect in relation to the sun is one of them. Now, sun is a good thing and a bad thing. It stabilizes and it destabilizes. We want enough to promote warm temperatures, which will lead us more towards rounding. However, if we get too much of it, it's a bad thing. And it then goes beyond stabilizing and becomes an unstabilizing effect. Here we have solar input in the spring. It's creating all these little avalanches here as we get our soft layer on top of a hard one. We've talked about faceting being promoted by cold temperatures, which is the lack of solar input. So lack of solar input is going to allow faceting to continue, which is why we'll probably get more faceting on a north-facing slope during midwinter than we will on a south-facing slope. Once we get to spring, then we get too much solar input on that south-facing slope, and that becomes more unstable through a type of avalanche that we'll talk about in a moment, a wet, loose one. But over on the north-facing slope, temperatures might be increasing, and we might be getting rid of those facets that have stuck around there. So sun depends very much on the time of the year and how much we get of it. So terrain evaluation. We talked a little bit about the parts of an avalanche path. We've got our start zone where things initiate. We've got our track where it runs and accelerates, then our run out zone where it stops. This is a photo from Canada. There's a highway at the bottom. These mounds here are put in by the highway department to, absorb the energy of that avalanche and prevent it hitting the highway there. So we've got start, run, and stop. Here we can see the avalanche has trimmed away the trees. And that's going to be one of our big clues for avalanche paths. Where has the avalanche trimmed the trees? Where's it eliminated them? and where's it left them. So that's always a good clue. We're looking for what we'll call flag trees, such as this. The limbs have been torn off on the uphill side and they might be lying in the snow somewhere. Now, avalanche was up to this level here, left the limbs above. So we'll often see these flag trees. We'll even see them in the summer, if our eyes open enough, because we're not thinking avalanche that time of year. We're also thinking about what's below the surface. And that's where, I'm lucky because I spend time in the same places. It's difficult when you're coming from out of the area. We'll ask ourselves, how well is the snow going to anchor to something like this? And that will lead into another type of avalanche problem, a glide avalanche that we'll talk about in a bit. So it's not going to stick well to this, a big granite slab. It will stick to this rough surface here of the talus. However, as we get more snow building up, it becomes less relevant and will reach a point where the talus is covered and it's no longer anchoring, and we're effectively back to where we were with the granite slab, the sliding surface. So those are things we're thinking about with terrain. We'll also think about what we call trigger points, which are places on a slope where an avalanche can initiate. So we're thinking about that because we want to know where those might be, and then we can put them into the consequence of one, should it occur from one of those trigger points. Now, trees and shallow rocks can be a trigger point. Let's look at this image here and think back to what we talked about previously with our indirect effects below the surface. We've got a rock poking through here that thins the snowpack. So we've got deeper snow here, we've got shallower snow here. Our air temperature is the same over the whole snowpack. Thinking back to what we talked about previously, what type of snow grain do you think we might get developing around the rock that we mightn't get developing out over here so much? Type it on in for me. You've got two choices. Faceted for Carlos. Yes, exactly. So that's why the rocks can act as a trigger point, because we're more likely to get faceted snow around them. Trees. We think, trees give us a warm, fuzzy feeling. We like them. They give us an aura of safety. They're not. They act as effectively the dots in a dotted line, weakening and disrupting the snowpack. So trees can also be trigger points. Again, the rocks, when we look at this image here, we've got rocks here where it could have get faceted snow formed around them. It weakens it. Perhaps the skier just hit one of those points and triggered something. This one here, we've got a rock poking through. This here could have been the trigger point. Often what we find is that there's a weak patch, a weak point within the snowpack. From that, we can trigger something. Then it does what we'll call propagate, which is move through the snowpack, or that failure can move through the snowpack. Convex rollovers, there. Those can also be a trigger point. The snow is kind of under tension at the top there. At the bottom, we also have the snow under compression, which is also an area of stress. With our convexity stress at the top, it can be under tension. We go in there, we add a little more load to it, and that's enough to cause a fracture. That fracture can then propagate. So convexities are things that we can definitely trigger. And that's something that we factor in when we're looking at a snow slope. Maybe we're at the top looking down, we can see convex rollovers, we can see something that doesn't have them. We might choose to ski or ride where there aren't those convexities. We also have a concept here called remote triggering. And this one's kind of a spooky thing. Remote trigger basically means where we can trigger an avalanche at one point, but it occurs at a different one. In this image, we have a couple of avalanches here, but all the ski tracks are over this side here. So looking at that a little bit more in detail, we always have, or let's say, we can have a weak layer within the snowpack. We've got a weak layer in here, this layer here, there. It's all over the flat and on the slope. When we ski or ride, we always have what we call a stress bulb underneath our skis. It's where our load is affecting the snow below us. In this instance, our load goes down from our skis or our board or our snowmobile or our snowshoes. It gets to that weak layer. Let's imagine that our weak layer, our little surface hores poking up. Our extra load causes them all to fall over. As they fall over, the snow settles down. As it does that, air that's in the snow is compressed and moves out. And that gives a sound called a whoomp. And that's actually used as a technical term now. It's basically the snow being expelled from the snowpack. And it should get your attention very quickly. That failure can propagate all the way along that layer. It goes out, propagating, it gets to where the snow's under tension at our rollover, and it fractures there, although we've initiated it there. In this instance, it doesn't matter from an avalanche danger because we're above it. Let's now imagine the same thing happening at the bottom. We're skiing across here below the slope. There's that weak layer. We trigger that. Now the shock wave moves upslope, triggers this, and we're below it. The remote triggering is a real thing, and it can be a problem, particularly when we have these weak layers within the snowpack. These weak layers can be related to the persistent grains we talked about before of facets, depth hoar, buried surface hoar. So things kind of work together. If we know that we have this problem existing, we'll plan our route so it doesn't take us below these types of slopes. And we'll talk more about that when we get into our avalanche problems. This here is in Alaska, backside of Mount Dickey in the Ruth Gorge. I was on a climbing trip there a number of years ago. We came up from the right side of the photo here. I stepped onto the flat here. There's a whoomp, and a couple of seconds later, this fractured here. I would imagine that if we've got weak layer here, that weak layer exists all the way across this slope. We were climbing Dickey. I elected for us to continue up the slope over here. There's a number of things that were in our favor. We had a flat area where we could put people over here. This slope angle was less than over here. It was short up to the top where it flattened out. We could watch people go individually. We had avalanche beacons and equipment. When we look over here, there's also a big crevasse right there. So although this avalanche is fairly small, it could take somebody into that crevasse if you were over there, say traversing this slope. So we had a number of things that I felt we could use to mitigate the hazard. If any one of those had been lacking, we wouldn't have gone on up further. The hazard that, or the problem that existed here probably also existed over here, but I thought we could manage it and continue on up Mount Dickey, which we did. So part of it's recognizing the hazard and then figuring out if we can deal with it and how we can deal with it. The crevasse here is what we'll talk about in terms of being a terrain trap. And it's a feature that increases the consequences if we're caught. If you'd been traversing this slope and that avalanche had come off and taken you down there, it would have been a totally different scenario to it happening over here. Much more serious. So terrain traps can be a number of different things. Gullies and drainages. Now, a small amount of snow depositing, coming off a large area, depositing into a small confined area. Road cuts can definitely be a terrain trap. The terrain is steep above them, then it flattens out. We often think that a road cut gives us a warm, fuzzy feeling again because we think we're on a road. People do get avalanched on roads. Cliffs. A small avalanche can take us over a cliff and exaggerate the seriousness of a fall. Creeks, we can get swept into those. And trees. As I said, trees make us feel good. We think that, oh, I can grab a tree. In reality, we're not going to. And more commonly, people get taken down by an avalanche into a tree, and that's when they sustain traumatic injury. So parts of their body, their chest, their head, hits a tree, and that's when we have a problem. Cornices. Here we have a crack going around there, and somebody's gone off and stepped over it. Cornices, as I said, every single cornice has its day and falls off one day. So those are all terrain traps. We're constantly asking ourselves, are we in the run out? What's going to happen if an avalanche occurs? This is Mount Morrison, Convict Lake area. And you can just see Convict Lake there. You can come up this gully. It's fairly commonly done as an approach. And you can see avalanche debris in there. This here is what it looks like above all that terrain. This is Mini Morrison. Lots of fractures there. A couple of years ago, two guys went into Mammoth Mountaineering and asked my friend there, John, where should we go? And John said, oh, well, no, avalanche danger is high. I'd stay down low in the trees. One of them said, sounds like a good plan. We don't want to happen today what happened yesterday. So, of course, John said, what happened yesterday? They came up the gully here. They'd evaluated it and said that the slope angle here is only 20 degrees. Therefore, we're not in avalanche terrain. They're not in avalanche start zone terrain. As they came up here, I don't know if they remotely triggered it or if it's natural, but an avalanche came from above. It landed on top of the guys down here. One guy was buried to his shoulders. The other was buried to his knees. They managed to dig themselves out and went back down. So looking at this photo here, how do you think we could avoid that terrain trap by using a good travel technique? Type it on in the box there for me. What do you think? Where can we go to avoid this problem? What do you think? Go for it. Somebody can make a guess. Where's our best place to travel here to avoid the terrain trap? Stay out in the sun. Yeah, stay out on this side of the valley. It doesn't take much. We don't have to stay down there. We can just cut up and along the side. It might be a little bit more difficult terrain. Might have to side hill, but we're out of the run out zone. As I said, some of this stuff isn't that difficult. So we're trying to avoid the avalanche terrain where we can and assessing the run out zone, the start zone, and as we'll talk about in a little bit, we can apply travel techniques to mitigate our danger. So when we look at our terrain, as we talked about before, we'll go ahead and define our red flags. So our red flags for terrain, similar to what we did for weather and snowpack, slope angle. Are we getting, slope angle 45 or down to 30? Are we getting wind loading? Could be cross loading or top. Where are the lee slopes where a slab could exist? Are there trigger points? Are there rollovers? Are there rocks poking through? We'll relate this also to our avalanche forecast. Is there a potential for remote triggering? So are there terrain traps? Are we going to have to go through a narrow gully with steep slopes above us? Aspect in relation to the sun. Is that slope getting beaten on by the sun or is it not? Do we think that the facets are persisting because there isn't any sun. Aspect in relation to the sun depends very much on the time of the year, and particularly in the spring, when we're getting strong radiation for prolonged periods of time, which was one of our weather red flags. So we're trying to draw all of this together. So any questions on our terrain? I know there's a lot to look at, and it takes time to be able to come up with or be able to get experience in evaluating terrain. So is everybody good there? Any questions?
I think I've heard in the past that trees and rocks can be slab anchors. But I think, you know, you've shown that it's a very specific kind of direction to not either trust them as anchors or, you know, as exclusively trigger points. Yeah, what's your, I guess, opinion on that one?
Trees, as I said, are going to operate more as a dot in the dot of the dotted line. They're going to be an area of weakness. Trees will anchor, however, they need to be dense in order to do that. And as a general rule of thumb, if we can ski or ride through the trees fairly readily, so too can an avalanche move through them, and they're not going to be an effective anchor. No, to anchor, they probably need to be something denser than we want to deal with. As far as rocks go, the rocks will probably act more as a weak point, a trigger point, than as an anchor point, unless we have a very rough talus slope, unless it's early season.